we would like to call our next speaker, Raju Hazari. His paper name is A New Notion of Universality in Respect of Logic Gates Generation Capability of ECAs. He is from Department of Computer Science, NIT Calicut, India. So Raju, over to you.
Thank you, Sukurnadi.
Raju, can you turn on your video?
Yes. Okay. Am I audible?
Yes, yes.
Hello?
Yes, you are audible.
Okay. Thank you.
Please continue.
Okay. So, good morning, everyone. Myself, Raju Hazari. Today, I'll discuss, I will present my work. Name is title as A New Notion of Universality in Respect of Logic Gate Generation Capability of the ECA. So, in the beginning of this talk, I will discuss about some literature or talk about universal combination capability of elementary cellular automata and logic gate generation capability of cellular automata. Okay. So since 1980, elementary cellular automata have received wide attention from the researchers due to their simplicity and capability of the modeling physical system. And ECAs is the so ECAs are the simplest cellular automata, that is systems where the systems are actually binary, one dimension, and where the behavior of the each cell depend on itself, its two and its two nearest neighbor. Okay. Now, in respect of universal capability of the elementary CA, in 1984, Stephen Wolfram made a conjecture that ECA 110 is capable of universal computation. Okay, and that is the conjecture is made by Stephen Wolfram in 1984. Later, in 2004, the computational university of this rule, that is ECA 110, has been proved by Cooks. Okay. Now, in 2006, Martinez et al. Have advised that the ECA 54 will make a good alternative to ECA 110 in a sense of logical universality as well as the simulation of a Turing machine. So these are the few literature work I found, that is researchers actually prove that ECA rules are capable of universal computation. Now, in respect of design of logic gates generation capability of the CA, the design of logic circuit using cellular automata have been initiated from long back. It's actually from 1986. In 1995, Melanie Mitchells et al. Have constructed and or not gates by the using of Glinder guns. Okay. According to that work, when two glinders are collides, they annihilate, and this is actually used to build NOT gates. So they actually use the concept of collision of two Glinder guns. Okay, from that they are try to build the logic gates. So similar concept they are using for build the AND and OR gates. Okay, in 2018, Martinez et al. Also present the same the design of logic gate, so which is also implemented via collision between the glinders. So these are the few words where people are using Glinder guns to generate the logic gates, and both the cases are people are using the collision of the Glinder guns, and from that they are trying to find the logic gates. Okay, construct the logic gates. In 2008, Bidlow et al. Has introduced a evolutionary development techniques for designing the combinational circuit by exploring one-dimensional CA. So this is the first work that people are actually using the evolutionary development techniques for designing the logic combinational circuit. But in this work, the traditional concept of cellular automata was modified in order to generate the circuit at the gate level during the development of the CA. So we also, in our work, we also follow the evolutionary approach. So that means we are also evolve the CA to generate the logic gates. So that is we are, or that is that we when we when you use this approach, we first take it for rule 184, and we observe that ECA 184 can implement any logic gate. That means in this work, we found that all the basic logic gates such as AND, OR, NOT, NAND, NOR, XOR, XNOR, all can be realized by the evolving of ECA 184. And for that reason, we call that ECA 184 as a universal logic gate generator. So we define our universality in respect of the gate generation capability. That means we can say that a ECA has universal property when this ECA rule is capable to generate all the basic logic gates. And in such a way, we define actually the universality property of elementary ECAs. Okay, so this is our concept of universality. How we can say that a ECA rule is a universal computation capability. Okay, and this present work means that this or dot which are present here. This work is the
I think there is some connection issue from the speaker's side.
Hello.
Yeah, now it's good. Yes.
Yeah, sorry, there is some network. There is some power failure problem. So, okay, I just connect from mobile data. So, okay. So I hope it is audible, correct? It's audible.
Yes, Raju, audible.
Okay. Okay. So in this work, we also this work is the extension of our previous work, and where you all study explicitly the gate generation capability of all the ECA rules. Okay. So before we discuss about the our main work, we just discuss some basics about elements. So I hope you know these things. So, but I just given the brief discussion about ECA. So ECA is a one-dimensional array of finite state automata, and thus automata takes two states, that is 0 and 1, and it updates their states simultaneously in discrete time by using the next state function. Okay, so this is the simple block diagram for a element CA, that where the cell I, the next state of the cell I is depend on the three neighbors, that is itself and left and right cell. So that means if we consider cell I, the next state of the cell I is depend on cell R minus 1 and cell I plus 1. And how we calculate the next state, our next state function, that is SI t plus 1 equals to that is SI, the fi of x I minus 1 t SI t and I plus 1 t. So this SI minus 1 is SI minus 1 t and SI t and SI plus 1 t are the present state of left neighbor cell and right neighbor of I cell at time t. And this next state function fi is known as rule of the CA. Okay, so there are 256 such ECA rules are possible. Okay, now in our work we use actually a minimal representation of the rules. So what is minimal representation of the ECA rules? So we see that some researchers are identified that CA rules have equivalence. That means the same behavior we can find kind of in a set of rules, and we usually consider this minimal representation of each set as a set, and that is the we call it the minimum dependency of ECA rules. We can find that 88 such a minimal dependency of rule. So we see that within 256 rule we can represent the 88 minimal dependency rules. And in our work, those actually the behavior of the all minimal dependency rules are similar. So in our work, we only consider 88 minimal dependency rules. Okay, so that's so beginning of our work. So what do we do? So first we did that. First we represent ECA as a n input n output block. So that means, what does it mean? That we have used CA as a compression circuit block, and we consider n cell rule RCA as a R block. That means we consider a n cell CA as a n cell CA is a RCA actually is a R block like this. That means how represent that that initial configuration of the CA are the input to the blocks. That means this is the CA block, n-bit CA block, and the initial configuration, that is I1 to IN, we represent as a input of this block, that is I1 to IN. Okay, and a CA block inputs this I1 to IN to n inputs, and we represent we convert it into n outputs, that is O1 to ON. Okay, that means the CA block maps that n inputs I1 to IN to n outputs O1 to ON, and this is the block representation of this n input n output blocks. Okay, now we take an example for 3 input 3 outputs rule 57 blocks. So if you consider CA 57, and if you consider 3 input 3 output, that means there is a 3 input, we may consider this is X, Y, Z, and corresponding output you may consider like O1, O2, O3. This is the output. Now we can express this output variable, that is O1, O2, O3, of this 3 input 3 output rule 57 blocks as explicit function of input variable. That means we can represent, we can express these functions, this O1 as an explicit function of this variable, that is X, Y, Z. Okay, so how we do these things? To do these things, we first evolve the CA. Okay, so first evolve the CA and then we build the truth table. Okay, so now the question is how to build the truth table after evolve the CA. So next is that is the way how to build the so if we take this 3 input 3 output rule 57 block and we do the first evaluation, then how we get this truth table after first evaluation. So here we see that I1, I2, I3, this is the inputs, and O1, O2, O3, this is the outputs. Okay, now what does the input represent? That is the initial configuration of the CA. Okay, so if we take the initial configuration of CA is 0, 0, 0, then after one evolution we get 1, 1, 1. So that is actually our O1, O2, O3. Similarly, if we take initial configuration as 0, 0, 1, so after one evolution, after on time evolution, that will get the next state is the 1, 0, 0. That is our O1, O2, O3. Similarly, we take all the initial configuration, all 0 to all 1, and we get similarly the next configuration, which is our O1 to O3. So in such a way, we construct our truth table. So similar way, we can construct the truth table for second evolution. That means here we take all 0 is our initial configuration. Now after second evolution, we take the O1, O2, O3. So after 2 time evaluation, 2 time steps, what are the configuration we get? We consider as a O1, O2, O3. So here we see that if we consider this is the initial configuration 0, 0, 1, then after first evaluation, what do we get? That is 1, 0, 0. So that is the value of O1, O2 in this table, in this truth table. But after second evaluation, we get the configuration 0, 1, 1, 0, 0, 1, 0. That is the that's why these are the O1, O2, O3 in case of after second evaluation. In such a way, we may evolve third times, we may evolve 3, 4 time steps, and we can construct the truth table. Okay, so we have in the I1, I2, I3, we just take the initial configuration, and when we want to construct this truth table, after how many evolution you want to construct this truth table, then that is the configuration we write in O1 to O1, O2, O3. Okay, so after this construction of this truth table, we can easily write this O1, O2 in a form of some input variable. So in such a way, so we can get the what is the O1, what is O2, and what is 3. So for 57 for rule 57 3 input 3 output rules 57 blocks, after first evaluation we get these 3 functions, that's O1 equals to this one, and O2 is this one, and O2 is this one. And similarly for second evolution, after second evolution, what is the O1? We get O1 equals to xz plus x bar y. Similarly, O2 equals to xy plus y bar z, and O3 equals to yz plus xz bar. So in such a way, we get the actually this function, this value. This means this this O1, O2, O3. Okay. So in this way, we find out the output of the n input n output CA block. Okay, so that means we first evolve the CA, then we build the truth table, and then from the truth table we get the output function of any n input, n output, a CA block. Okay, and these output functions are actually we are used to design our logic gates. Okay, so how we design the logic gates? From this output function, we set some inputs, and then we try to design the try to get the our desired output, that is try to get our some logic function of some basic logic gates. Okay, so by proper selection of input, it might possible to implement AND or NOT, NAND or XNOR is XNOR, but by n input and outputs CA block. So we set some bits and then we try to realize this basic logic gates. Okay, so during this realization, we take a desired output from O1. So what the function logic gate function we want to take, that is we'll take from our this O1. Okay, so it is not mandatory that we have to take always from O1. You can take it from O2, O3, or maybe if it's n bit, then we can take from ON minus 1, whatever you want. But the thing is that in our work, I take it from O1, and based on that I set the value, input value. So when if you want to take output from other than on then you have to set the inputs as accordingly. Okay, so one can take desired output from output other than O1, but we need to set input variable in different way. Okay, now let us see the example that how we see that here you see that the gate generation capability of ECA 57. All the gate here you see that ECA 57 is capable of realize all the basic gates. Now how we realize? So I want to discuss one by one. So if we see for logic NOT, so how we get logical NOT for by using ECA 57 ECA 57, that is for we use 3 input 3 output ECA 57 block, and we set 2 bits, that is X and Z equals to 0. Then from O1 we get actually the logical NOT function. So that means we set X and Z equals to 0. So if you see the function, output function O1 here, and if we put X and Z equals to 0, so if we put X equals to 0, then means this term is 0, and if we put Z equals to 0, this term is also 0. Now we remaining, this is there the only one term, and here we put X equals to 0, then this is O1 and this is Y dot. So actually the output function what I get, that is O1 equals to Y dash, Y dot. So that is actually the logical function of NOT gate. So in such way we get the NOT gate. Similarly, and we get this after first evaluation. So if we set like this the initial configuration of the CA, then after first evaluation we get the output from O1. That is the concept of how to get the realize the logical NOT. Similarly, for logical XOR, we set single bit, that is Y, Y equals to 1. So if you and after first evaluation we get the output. Okay, these are output, that is Z bar plus X bar Z. So how we get it? So if let you consider that we set Y equals to 1. So if you set Y equals to 1, then after evaluation, first evaluation, these are the function. So we only consider O1, so we check this O1. So Y equals to 1. So if Y equals to 1, then what is this one? This one is X Z bar, and this is X bar Z. And if we put Y equals to 1, then this term is 0. So actually we get Y1 equals to X Z bar X bar Z. So this is the function of a logical XOR. Okay, so that's why I get the logical function. If we set the inputs like Z Y equals to 1, then we get the logical XOR function here from the O1. Okay. Similarly, if you want to get logical AND, then we have to set Y equals to 0, and you have to evolve the CA 2 times. So all such like logical NOT, FANOUT, and XOR and XNOR, we just evolve the CA single time. But here we have to evolve the CA 2 times. So what we did here, we set the y equals to 1 or y equals to 0, and then we take the output, and then we have to evolve the CA 2 times. So if you consider y equals to 0, and if you see this function, so these are the function, after second evolution we get this function of, so y1 equals to, we get y equals to 0. So if we put y equals to 0, then what happens? This term is 0, so we only get y1 equals to o1 equals to x z. So that is the logical function of AND gate. So after second evolution from o1 we get the logical function of AND gate. Similarly for NAND gate, we have to evolve the CA 3 times evolution. Okay, so when we want to get the logical function of NAND gate, that times you have to set x equals to 1, and then if we evolve 3 times, then we from o1 we get y bar plus z bar. So how we get? Let's set x equals to 1 in, so that's actually this function is not written. So if such a same way what I did for explain that for a logical AND, logical XOR, same thing we can do, and we get the NAND gate function and NOR gate function. So we see that to realize all the basic logic gates, just like NOT, NAND, NOR, NAND, or like all NAND, all those things, we use some CA block. We use CA block and input and output CA block, and then we use different number of steps to get the desired output. So for rule 56, rule 57, we see that to realize all the basic logic gates, 3 input 3 output block is sufficient, but it is not true for every ECA rule. So sometimes it's required 4 bits CA, sometimes required 5 bits CA, sometimes required 6 bits CA. Even and also see that to get the desired output, we have to evolve the CA different number of times, means different evolution. Means some gate we can get after first evolution, some gate we can get after second evolution, some get after third evolution. Similarly for different size of CA also we have to earn CA with a different time evolution, and we get the desired output. For if you consider for ECA 184, we need 5 block, maximum 5 block to get some gates. Okay, so it is not like always we get always we realize the basic logic gate function by using only 3 input 3 output board and only 1 or 2 evaluation. It may possible to, we have to evolve 4 times, 5 times. Okay, yeah, maybe we have to record n times also. Okay, so that is depend on the which rules are we use and which size of the block we use. Okay, so this, in such a way we realize all the basic logic gates by a ECA. Okay, and this is an example of how to realize the basic logic gates by ECA on 57. So we explored the logic gate generation capability through evolution of the ECAs, and after that, after we find out check the evolution of this gate generation capability of the all 88 ECA rules, we find out that within 88 equivalent rule, there are only 28 rules which are capable to realize any logic gate. That means there is only 28 rules that is noted in here. These rules are capable to realize any logic gates. That means we can generate all logic gate function from these rules. But we have to evolve the CA in different times. So you have to take the size of different size of CS blocks. Okay. Now after getting this list, the 28 minimal rules are capable of capable of generating all the logic gates. Now we compare the within these 28 ECA rules, which rules are the based on. So for that, to compare the logic gate generation capability of these rules, these 28 minimal ECA rules, we consider 2 cases. One is average case, one is worst case. So in average case, we consider 2 parameters. One is total number of bits required to realize all the logic gates, and total number of time evolution need to design all the logic gates. What does it mean? The total number of bits required to realize all the logic gates. That means for a particular gate, to realize a particular gate, we need maybe 3 bits CA or maybe 4 bits CA. So that is the 3 bits requirement for a single gate. So in such a way, we have to check all the 8 logic gates and sum of the total bits requirement for design all the logic gates. That is the total number of bits required for to realize all the logic gates. So just like for what I discussed in ECA 57. So in ECA 57, we see that for all logic gates we required for 3 bits here. So that means the total number of bits required for ECA 57 is 3 into 8, that is 24. Okay, and total number of time in evolution need to design all the logic gate. That means for realize on single logic gates, how many times we have to evolve the CA. That is the number of time evolution required for a realize on single logic gate. So we have to add all these numbers to realize all the logic gates, and that is the total number. Okay, so if you see this rule for ECA 57, then what is the total number of time evolution required? So there is single time evolution. So there is 4 gates. So this 1 into 4, that is 4, and this is the second 2 time evolution required. So this is 2 into 2 means 4. So 4 plus 4, 8, and that is 6. So 8 plus 6, that is 14. So total number of evolution is required to realize all the logic gates in case of ECA 57 is 14. Okay, that is the total number of time evolution need to design all the logic gates. And in case of OR's case, we also consider 2 parameters. That one is the maximum number of bits required, and another one is the maximum number of evolution need to design the gates. So maximum number of bits required means, if you consider the same example, that is ECA 57, then what is the maximum number of bits required? That is 3. Within 3 bits we can realize all the logic gates, but it's not necessary that always requires 3. So for if you consider ECA 184, that in that case we maximum 5 bits required to realize all the logic gates. Okay, so maximum number of bits means what is the maximum number of bits is required to realize the all the logic gates. Okay, and maximum number of evolution need to design the logic gate. That means what are the maximum time step is required for design any gates of this for this year. So if you consider ECA 57, then maximum time evolution required is 3. So maximum number evolution need to design logic gates for 57 is the 3. Okay, so based on these two cases and these 4 parameters, we get the result. So that is the 28. This is the 28 ECA rules which are capable to generate all the logic gates, and this is a corresponding with OR's case and average case and OR's case. And average case we consider 2 parameters, there is total bit and total evolution. This is the number for each ECS, and we all in OR's case we consider 2 parameters, that is maximum number of bits required and maximum number of evolution required. So these are the numbers for each all the 28 ECA rules. And so in respect of average case, so with respect of in average case, with respect to less number of bits required to generate all the logic gates, we see that ECA 57 is the best ECA rule. So if you see the total, what is the total number of bits required? If you see in this list for ECA 57, 24 bits are required, because all logic gates you can generate with 3 input 3 output blocks. So total 24 bits are required. So in respect of with respect of less number of bits required to generate all the logic gates, ECA 57 is the best ECA rule. Similarly, with respect to total less number of time evolution required, ECA 73, 104, 106, and 134 are the best ECA rules, because if you see the total number of evolution is required, if you see that in 73 there is 11 total evolution is required, 11. For ECA 57 is required 40. But in 73 is required 11, and also for ECA 106 is required 11, and for 134 is also required 11. So is that for in respect of total evolution, total number of time evolution is required, this 73, 106, and 134 is the best ECA rule respect of less time evolution. Okay, so in case of OR's case,
you are requested to wrap up quickly.
Yeah, it's within 1 minute. Okay, within 1 minute. So in on OR's case, you also consider 2 parameters, that is maximum bit required and maximum number of time evolution required. So in this, with respect to maximum number of bit required, so maximum number of bits required means we say maximum number of bits required, but we consider the less, which is in case which was the less bits required. So which is the best ECO? So in that respect, we see that ECA 57 is the best ECO, because if you see here, the maximum bits is required in case of 57 is 3. So if we say the in the base rule in respect of maximum bit requirement, then ECA 57 is the best ECA rule. Okay. Similarly, for with respect of less number of time evolution required, okay, that is that in case we can see these are the rules that 41 is required 2 evolution, that is 62, 73, 94, 104, 106, 1010, 122, 126, and 134, and this 156. These are the rules are the best ECA rules in order to design the logic gates in respect of less number of time evolution. Okay. So I come to the conclusion of this work. So that is, in this work we have shown the gate generation capability of all the elementary cellular automaton rules. And in the beginning of the study, what I said, we explored the gate generation capability of 88 minimum ECA rules. After that, we compared the gate generation capability of the ECA, all the ECA rules, and we have shown that out of 88 minimal rules, the 28 rules are capable to implement all such logic gates, all the logic gates. Okay, so we can say that these 28 rules has universal property. Okay, in respect of logic gate generation capability. Okay, so these are the few references I used, and thank you.
Thank you, Raju, for your nice presentation and nice talk. So now the audiences are requested to ask the questions.
Raju?
Yes.
Yeah. Have you thought of creating some kind of circuit using this blocks
Yes.
that you have developed?
Yes, actually, in case of EC 184, we also did these things. That is, we also designed some just like a multiplexer, adder, full adder, half adder. We also designed by evolving the EC 184. So similar concept I also thinking about to these rules also, these other 27 rules also, but till now it's not complete. So just my aim was to take that these rules are because these rules are capable of realize any logic gate. So that means that these rules are also capable to realize any logic circuit. So
yeah. So you might also do that in a say in a logic circuit implementation. For one part you are using block used by one rule, and for another part you are using another rules block. That is also possible. Making
yes, that is also possible. That is means you are saying about programmable CA like this. That is some part programmable CA like
not
that.
Programmable CA. I am saying that say you are designing an adder circuit. Then okay. For the adder circuit, some blocks will be required. No, some AND will be required, OR will be required. So
no, actually, in such a way you can also design, but I saw
also you can design.
Yeah, if we take simple gate and mixed up, and then we can generate the adder function. But you also see that if we take just like 5-bit CA and we evolve the CA, then we get the actually adder function. Okay. So it's not like you have to take symbols. We can construct. If we know that if we know the logic function of the basic gate, so from the basic gate we can generate the adder function. That is true. But instead of like using basic gates and to the make the circuit, instead of that we we actually take simple 5-bit CA and then evolve the CA and then get some bits, and then we realize the adder function. That is also possible. Okay.
Thank you. Nice.
I have a question.
Yes.
Can you implement any buffer register using that? Then we can implement some CA with memory like logic.
I'm also thinking, but I'm not till now implement. Means I also thinking like register all these things.
I think,
but I have to check
if we can implement any kind of flip flop using that, then we can go for it maybe.
Yes, I will try it. It means I have not checked it yet, but I have to see this.
Okay.
Any more question?
I want to add, I mean, what Kamalika and Subhot was saying. So Raju, my question is,
Sir.
see, yeah, you are. It is true that since you can generate all gates, it's possible to develop any circuit.
Yes, sir.
But that is not the maybe that is not the way you want to implement. I mean, you want to evolve, and based on that, you want to get some function, right?
Yes, yes.
So my question is, can you think of the design of say ALU, arithmetic logic unit?
That is my ultimate aim, sir. But in that case, we have to design all such function like adder, multiplier, like division, all those things by the CA. So that is our target, but I have to check, sir, how much possible.
But may not be the all functions may not be multiplier or the divisor, etc. Maybe with adder and some minimal ALU you may develop using the 27 CAs which you have identified, ECAs which you have identified.
28, sir.
28 CAs which you have identified, using some combinations of them or taking some help of other. I mean, what do you think? It is possible to develop an ALU?
I think so, sir. I believe on that it may be possible to design ALU using cellular automata. So in this, I also thinking to work on that direction. So it is our future goal, sir, to
that might
design some ALU using CI.
That might be a good research direction in future. Thank you, Raju.
Thank you, sir.
Okay, any more question? Raju, I have just one query. So as your target is to just develop say 1-bit cellular automata, sorry, 1-bit adder. So in that case, when you are considering in-bit adders, so what will be your approach? Say in-bit carry propagation adder or in-bit carry lookup adder?
Actually, my concept is same like this, means that we have to take a string of rules, state, like maybe n-bit state, and by a rule, by maybe it's not if it's not possible by the ECA, maybe we'll design the rules, okay, and then we evolve the state. Means my approach is to, by evolution, we can we realize all this function by the evolution of the CA. Means after certain evolution, you can stop and say, oh, okay, this is our desired output result. Understand what I'm saying?
Okay.
So for that we may consider n-bit cell CA, and then n-bit rule, maybe it's uniform, non-uniform, whatever we can use, and then you evolve the CA, and then after we finally reach out after certain step, and then we can decide, okay, these are our desirable output. This is our approach actually.
Oh, thank you. So any more questions from the audience side? So if no more questions, so we can end our session here.